Hello everyone, welcome back to my YouTube channel. In this week's video, we are going to discuss 8 different questions ranging from chapter 1 till chapter 4. So let's get started. Question number 1. At the beginning of a reaction, there is a heat transfer of 60 joule to a system while the system does 15 joule of work. A moment later, 23 joule of heat was transferred out of the system while 3 joule was done on the system. Interpret this information to determine the net change in the internal energy of the system. Alright, so before we can do this question, we need to look at the information given to us. So at the beginning of the question, there are heat transfer to the system, which is 60 joule, means that your Q should be positive 60 joule. And then it states here that the system does the work, means that the work is being done by the system, means that the W should be negative 15 joule, right? And then after a while, 23 joule of heat was transferred out. So when the heat was transferred out, it means that your Q should be negative 23 joule, and then the work, 3 joule of work was done on the system. So work is done on the system, so this one should be positive 3 joule. So what we are going to do is we need to find the net for the work and also the net for the heat transfer. So we are going to do the work first. So work, this one and this one. So the net of work should be 15 joule plus 3 joules. So you should get negative 12 joules. And then you are going to calculate the Q, which is the heat. So the heat, you have positive 60 joules, and then the other one is negative 23 joules. So therefore you should get 37 joule. Alright, after that, only you can find the question, the net charge in the internal energy. So the internal energy, which is U net, is equivalent to Q plus W. So you already calculated your Q, 37 joule, and your W is negative 12 joule. Therefore, you should get the delta U net should be equivalent to 25 joule. So this is the final answer for the first question. Moving on to question number 2. 10 grams of iron bar with temperature of 353 Kelvin was dropped into 70 ml of water at 25 degrees Celsius. If the final temperature of the iron bar was 298.85 Kelvin, identify if the specific heat capacity of iron bar is lower than water, given that the specific heat capacity of water is 4.184 joule per gram per degree Celsius. Alright, so in this question we have two main parts, which is the iron bar and also the water, and we were asked to calculate the specific heat capacity. So the best formula that we can use is Q equivalent to Ms delta T. And then according to the first law of thermodynamics, so Q water plus Q iron should be equivalent to 0. So what we are going to do now is we are going to plug in all the values that we have from the question. We're going to start with water. So we have 70 ml of water. So due to the density, so 70 ml is equivalent to 70 gram. And then the heat capacity of water is given in the question, which is 4.184. The unit is in joule per gram per degree Celsius. And this shall make the temperature should be in degrees Celsius as well. So delta T is final temperature minus initial temperature. So your final temperature is actually equivalent to the final temperature of the iron, because we assume that it is already at equilibrium. So 298.85, you need to minus 273 because you want to convert this into degrees Celsius minus the initial temperature, which is 25 degrees Celsius. Right, we are done with water. And then we are going to move on with iron. So the iron, the mass is 10 gram. The heat capacity is what we are going to calculate. And the final temperature is 298.85 minus 273 minus the initial temperature is 353 minus 273. So make sure that you need to convert the temperature to degrees Celsius because if not, it doesn't match your heat capacity. So from here, we can calculate by using our calculator. So we have 70 times 4.184, which is the heat capacity of water, and then the delta T should be equivalent to 0.85 degrees Celsius. Plus, we're going to do the other side, which is for the iron. The mass is 10, S is the one that we are going to calculate, and the delta T is equivalent to negative 54.15. So altogether here, it should be equivalent to 0 because of the first law of thermodynamics. So once you rearrange all these values, so you should get the negative S for iron is equivalent to negative 2.4894 times 10 to the power of 2 divided by 5.4150 times 10 to the power of 2. Therefore, your specific heat for iron is equivalent to 4.5972 times 10 to the power of negative 1 joule per gram per degree Celsius. In the question, you were asked to identify if this specific heat capacity of iron is lower or higher as compared to water. So the specific heat of iron is equivalent to 0.45972 and the specific heat of water is equivalent to 4.184. Therefore, from here we can say the specific heat of iron is actually lower as compared to the specific heat of water. So this is the final answer for the second question. Moving on to question number 3. A total of 0.2436 gram of unknown substance was dissolved in 20 milliliter of cyclohexane. Given that the density and the freezing point depression of cyclohexane are 0.779 gram per mil and 20.2 degrees Celsius per molar respectively. By using their knowledge in qualitative properties of solution, determine the molar mass of the unknown substance if the delta T is equivalent to 2.5 degrees Celsius. In this question, you were given the density of the cyclohexane. So from the density, we can actually find the mass of the cyclohexane because it is being dissolved in 20 ml of this cyclohexane. So we need to know the mass so that we can calculate what is the molality of this cyclohexane. So given to you, the density is 0.779. So we need to convert it into the mass. So what we are going to do now is 0.779 gram per mil times the volume, which is the 20 ml. So you should get the mass of cyclohexane that is being used in this problem is actually 1.5580 times 10 to the power of 1 gram. So in terms of calculating the molality, we want the mass in kilogram instead. So kilogram to gram. So since our unit is in grams, so we need to divide this with 1. 1000, so you will get the mass of cyclohexane is 1.5580 times 10 to the power of negative 2 kilogram. Alright, this is the first steps. And then what else that we need to know is we need to know what is the Van Hoff factor for the cyclohexane. So cyclohexane doesn't dissociate completely. So we can say that the Van Hoff factor for the cyclohexane should be equivalent to 1. So given to you is the delta T freezing equivalent to Kf molality times the Van Hoff factor. So what else is given to you? You were given the value of Kf. So the value of Kf is given to you in the question, which is 20.2. So now we are going to calculate what is your molality. So delta T freezing is 2.50. Your Kf is given in the question, 20.2. So molality is the one that we want to calculate, and you know that your Van Hoff factor is equivalent to 1. Alright, so we need to know what is molality. So molality is mole of solute divided by the mass of solvent. But this mass of solvent must be in kilogram. So we already calculated the mass of solvent, which is the mass of cyclohexane in kilogram, equivalent to 1.5580 times 10 to the power of negative 2 kilograms. So what we are going to do now is we are going to plug in that value in here. So mole of solute divided by 1.5580 times 10 to the power of negative 2 kilogram. So times 1, which is the Van Hoff factor. So from here we can find the mole of solute is actually equivalent to 2.50 times 1.5580 times 10 to the power of negative 2 divided by 20.2 times 1, which is a Van Hoff factor. Therefore, you will get the mole of solute should be equivalent to 1.9282 times 10 to the power of negative 3. So this is mole. Alright, so in this question, you were asked to calculate the molar mass of the unknown substance. So you know already what is the number of mole. So number of mole is equivalent to mass over R and M. So the number of mole here is 1.9282 times 10 to the power of negative 3, and the mass of unknown substance given to you in the question, which is 0.2436 gram. So definitely you will get the RMM. So RMM is equivalent to 0.2436 divided by 1.9282 times 10 to the power of negative 3. So now all you need to do is you need to press your calculator and you will get the relative molar mass equivalent to 1.2167 times 10 to the power of 2. So this is the final answer for the question. So the unit for here is equivalent to gram per mole, because this one is gram, the mass, and this one is mole. So 1.2167 times 10 to the power of 2 gram per mole. Let's move on to question number 4. Express the ionic strength of mixture of 0.1 molar of magnesium sulfate and 0.2 molar of calcium chloride. So the first thing that we need to do is we need to separate this into its ionic form. We're going to start with magnesium sulfate, so we have Mg2 plus and also SO4 2 minus. And moving on to calcium chloride, we have Ca2 plus and Cl minus. So what we are going to do now is we're going to plug in all this value inside the formula for ionic strength. So the ionic strength is equivalent to half and the summation of the concentration times the charge to the power of 2. So what we are going to do is we're going to start with the magnesium sulfate. The concentration is 0.1 times the charge for magnesium is positive 2 to the power of 2 plus the concentration is 0.1 times the charge is negative 2 to the power of 2 plus the concentration now is 0.2. The charge is positive 2 to the power of 2. And the last one, the concentration is 0.2 times 2 because you have 2 chlorine here times the charge is negative 1 to the power of 2. So when you calculate this, you will get 4 times 10 to the power of negative 1 plus another 4 times 10 to the power of negative 1 plus 8 times 10 to the power of negative 1 plus 4 times 10 to the power of negative 1. Hence, you will get half times 2.0 and your final answer for the ionic strength should be equivalent to 1.0 molar. So this is the final answer for the fourth question. Let's move on to question number 5. The gas equilibrium constant Kp for the dissociation of nitrogen dioxide is 158. The partial pressure of oxygen gas produced was found to be 0.25 atm. By employing the information given, calculate the partial pressure of nitrogen dioxide at equilibrium. Alright, the first step that we need to do is we need to write a balance equation of the dissociation of nitrogen dioxide. So the nitrogen dioxide shall dissociate into nitrogen monoxide and oxygen gas. Up next, we shall make the ice diagram for this reaction. So for the ice diagram, initially we don't know what is the concentration of the nitrogen dioxide. So we are just going to put Y, and there are no dissociation occurring at the beginning of the reaction. So at change, we have negative 2x. This one is positive 2x and x. Therefore, at equilibrium, it shall be y minus 2x, 2x, and x. Alright, so if we read again at the question, it says that the partial pressure of oxygen gas produced was found to be 0.25 atm. Therefore, we can say that the value of x is actually equivalent to 0.25. Right, so what we can do now is we can substitute all the x's with 0.25. So we shall get at equilibrium, the value is as such. From here, we can calculate our Kp. So Kp is whatever in the product divided by whatever in the reactant. So partial pressure of oxygen times partial pressure of nitrogen monoxide to the power of 2 divided by partial pressure of nitrogen dioxide to the power of 2. So we are going to substitute all this value inside this equation. Therefore, oxygen is 0.25. Nitrogen monoxide is 0.5. So this one to the power of 2. And then you have y minus 0.5 to the power of 2 as well. And then given to you in the question, the Kp, the value of Kp is equivalent to 158. So your Kp is 158. Therefore, it's easy for us to find what is the value of y. Alright, so in order for us to find the value of y, the easiest way is to square root this one because we have to the power of 2 here. So we are going to make a square root of this. So leaving you with 1.2570 times 10 to the power of 1 is equivalent to 0.25 divided by y over 0.5. So now all you need to do is do the simple quadratic. So 1.2570 times 10 to the power of 1 times y minus 0.5 should be equivalent to 0.25. Hence, you should be able to get your y should be equivalent to 5.1989 times 10 to the power of negative 1. So, in the question, you were asked to find what is the partial pressure of nitrogen dioxide. Alright, so by referring to the ice diagram, at equilibrium, the partial pressure of nitrogen dioxide is equivalent to y minus 2x. Therefore, now what we are going to do is we're just going to plug in the value. So y is equivalent to 5.1989 times 10 to the power of negative 1 minus 2x, where your x is 0.25. Therefore, we can get the partial pressure for nitrogen dioxide at equilibrium should be equivalent to 1.9890 times 10 to the power of negative 2. So this is the final answer for the fifth question. Question number 6. An unknown compound has an empirical formula of C2H4O. Given that 0.23 grams of the unknown sample has a volume of 0.0785 decimeter at 95 degrees Celsius and 102 kilopascal. Identify the molecular formula for the unknown compound. The first thing that we need to do is to ensure that all the variables are in the correct unit. For instance, the volume shouldn't be in decimeter and the temperature should be in Kelvin, and we need to convert kilopascal into atm. So this is the conversion of the unit. Right, now we're going to use the ideal gas law, PV equivalent to nRT, to find the number of mole of the unknown sample. So the pressure is 1.0067 and the volume is 0.0785, and is the thing that we want to calculate. R is the gas constant, 0.0821, and your temperature is 368 Kelvin. So from here we can get your N is equivalent to 7.9026 times 10 to the power of negative 2 divided by 3.0213 times 10 to the power of 1. Therefore, you will get your N is 2.6156 times 10 to the power of negative 3 mole. So this is the number of mole of the unknown compound. So since we already know the number of mole, definitely we can get what is the relative molar mass. So number of mole is equivalent to mass over RMM, the relative molar mass. Given to you is the mass, which is 0.23 grams. RMM is the thing that we want to calculate, and the number of mole is 2.6156 times 10 to the power of negative 3. Therefore, your RMM should be equivalent to 0.23 divided by 2.6156 times 10 to the power of negative 3. Hence, you will get your RMM should be equivalent to 8.7934 times 10 to the power of 1. Okay, but the question asks you to identify the molecular formula of the unknown compound. So given to you is the empirical formula. So your empirical formula is C2H4O. So you need to put N here, should be equivalent to 8.7934 times 10 to the power of 1. Alright, so all you need to do is you need to look at the table to find the atomic mass for each and every element. So we are going to do the atomic mass and then you need to times the number over here. So you will get N times 4.4053 times 10 to the power of 1 is equivalent to 8.7934 times 10 to the power of 1. Therefore, you can get your N is equivalent to 8.7934 times 10 to the power of 1 divided by 4.4053 times 10 to the power of 1. Therefore, you will get your N equivalent to 1.9961, which is relatively equivalent to 2. So, since your empirical formula is C2H4O, so you need to put N here, whereby your N is equivalent to 2. So you will get 2 times 2 is 4, 4 times 2 is 8. We only have 1 oxygen, so 1 times 2 is 2. So therefore, this is your molecular formula of the unknown compound.
Let's move on to question number 7. Sulfur dioxide gas and oxygen gas were reacted in a 1.8 liter vessel to produce sulfur trioxide gas. This reaction reached its equilibrium at temperature of 585 Kelvin with a total pressure of 5.33 atm. Apart from that, 0.05 mole, 0.08 mole, and 0.07 mole of sulfur dioxide gas, oxygen gas, and sulfur trioxide gas were found at equilibrium respectively. By applying an appropriate formula, calculate the Kc for the reaction. First and foremost, we need to write a balanced equation for this reaction. The reaction consists of sulfur dioxide, which shall react with oxygen gas, and then it will produce sulfur trioxide. So we need to balance up this equation. So here we have 3 oxygen and here we have 4 oxygen altogether. So the best we can do is putting 2 here, making you have 6 oxygen altogether. So we put 2 here, so 2 times 2 is 4 plus 2 is equivalent to 6, and then we are going to look at your sulfur. Both sides now have 2 sulfur. So this is a balanced equation for this reaction. Next up, we are going to list out the number of mole of each substance. So from the question here, we have 0.05 mole of sulfur dioxide. And then we have 0.08 mole of oxygen. And lastly, we have 0.07 mole of sulfur trioxide. So from here, we can calculate the mole fraction. So the mole fraction is equivalent to the number of mole of that particular substance divided by the total number of mole. Alright, make it easier for us to see. I'm going to tabulate it inside this table. So the number of mole for sulfur dioxide is 0.05, followed by oxygen, which is 0.08, and sulfur trioxide is 0.07. Now we're going to find the mole fraction. So the mole fraction is 0.05 divided by the total number of mole, means that it's 0.05 plus 0.08 plus 0.07. So basically, we are going to do the same thing for oxygen and sulfur trioxide. So 0.08 divided by total number of mole, and here 0.07 divided by total number of mole, right? So basically, you should get the mole fraction is equivalent to 2.5 times 10 to the power of negative 1 and 4.0 times 10 to the power of negative 1, and lastly is 3.5 times 10 to the power of negative 1. So make sure that you write this clearly, means that, for example, for the last one, it should be 0.07 divided by 0.05 plus 0.08 plus 0.07. Therefore, you should get 3.5 times 10 to the power of negative 1. So next up, we are going to calculate the partial pressure. So the partial pressure is the mole fraction. So like here, mole fraction is 2.5 times 10 to the power of negative 1. You need to times the total pressure. So what is the total pressure? In the question given to you, the total pressure is 5.33. So you times 5.33 for each and every substance. Therefore, at the end, when you calculated it, you will get the partial pressure to be 1.3325. And for oxygen is 2.1320. And lastly, for sulfur trioxide is 1.8655. That is the partial pressure of each component or each substance related to this reaction. Alright, so moving on, here we can already calculate the Kp. So the Kp for this reaction is whatever at the product. So we only have one product. So partial pressure of SO3, because you have 2 here, so you need to do to the power of 2. And then the partial pressure of SO2 to the power of 2 as well, and the partial pressure of oxygen. So what we are going to do is we are going to plug in the values that we have calculated just now. So the partial pressure of sodium trioxide is 1.8655 to the power of 2 divided by the partial pressure of SO2, which is 1.3325, also to the power of 2 times partial pressure of oxygen is 2.1320. So basically from here, you just need to press your calculator and you will get your Kp is equivalent to 9.1929 times 10 to the power of negative 1. Alright, but this is not all, because you were asked to calculate the Kc instead of Kp. So what we are going to do is Kp is equivalent to Kc RT to the power of delta N. So how are we going to calculate delta N? Is equivalent to the product minus the reactant. So all of these are in gaseous state of matter. So we need to look at all of this. So at the product you have 2 minus the reactant, we have 1 plus 2. So 1 plus 2 equivalent to 3. So your delta N is equivalent to negative 1. Alright, so we know the value of delta N and also we know the value of Kp. The rest is just the constant, the gas constant, and the temperature is given to you in the question, which is 585. So now we're going to plug in the value. So your Kp is equivalent to 9.1929 times 10 to the power of negative 1, equivalent to Kc, the thing that we want to calculate. And your R, the gas constant, is 0.0821. And your temperature is 585, and your delta N is equivalent to negative 1. Therefore, your Kc is equivalent to 9.1929 times 10 to the power of negative 1 divided by 2.0821 times 10 to the power of negative 2. Alright, so from here you will get your Kc is equivalent to 4.4152 times 10 to the power of 1. So this is the final answer for the 7th question. Alright, we are now at the final questions for this week's discussion session. So the value of Kc for a hypothetical reaction of 2A to produce B plus C is equal to 2 times 10 to the power of negative 3. The initial concentration of A, B, and C are 3 times 10 to the power of negative 4 molar. Briefly explain which direction the reaction shall proceed to. So this is a rather simple question. Given to you is the initial concentration. Therefore, what you can calculate is the QC. So QC is equivalent to whatever in the product. So we have B and C divided by whatever in the reactant. Since the reactant is 2A, so A to the power of 2. And from the question, it says that the initial concentration of A, B, and C are the same. So what we are going to do is 3 times 10 to the power of negative 4 square divided by 3 times 10 to the power of negative 4 square should be equivalent to 1. So your QC is equivalent to 1. So given to you, the Kc is equivalent to 2 times 10 to the power of negative 3. And from your calculation, your Qc is equivalent to 1. From here, we can say that your Qc is bigger than your Kc. When your Qc is bigger than your Kc, it shall move to the left. It means that this is a reactant favored reaction. Alright, we have come to the end of this week's video. I would like to thank you so much for watching this video until the end. If you feel that this video is helpful, please give it a thumbs up and I'll see you again next week. Take care, be good, and stay safe. Goodbye.